This 2D plot maps the standard model Higgs potential in Minkowski space. Based on current measurements, a Higgs boson mass of roughly 125 giga-electron-volts and a top quark mass of 137 giga-electron-volts. Our universe rests here, in a local minimum known as the electroweak false vacuum. It is separated by an energy barrier from a much deeper negative energy state called the Planck scale true vacuum. In a static, geometrically flat universe, quantum fields fluctuate. Eventually, the Higgs field will tunnel through this energy barrier and decay into the true vacuum. However, calculating the probability of that tunneling event in flat space yields a timescale exponentially longer than the current age of the universe. This baseline understanding of the Higgs field, resting safely in a metastable state, relies heavily on the unified electroweak theory developed by physicists like Steven Weinberg. But the early universe was neither static nor flat. Physicist Alan Guth proposed that fractions of a second after creation, the cosmos underwent a period of violent exponential expansion known as cosmic inflation. This animation shows the background grid of our potential plot violently stretching into de Sitter space. During inflation, quantum vacuum fluctuations, represented as delta phi squared, do not remain static. They scale in direct proportion to the Hubble scale squared. Gravitational expansion acts as an amplifier. The local fluctuations of the Higgs field become violently agitated. Rather than waiting billions of years to slowly tunnel through the barrier, the field threatens to be instantly pushed over the energy barrier by the sheer kinetic energy of inflation. The geometry of the early universe takes a mathematically safe metastable vacuum and weaponizes it, turning cosmic expansion into a potential trigger for immediate cosmological collapse. To model whether the universe could actually survive this inflationary decay, physicists historically relied on stochastic Fokker-Planck equations. But in this extreme environment, that approach is mathematically inadequate. Fokker-Planck equations are designed to calculate long-wave modes. They inherently ignore the short-wave ultraviolet, or UV, parts of the quantum field. Short-wave modes dictate the actual effective potential of the field. Calculating the true decay probability under exponential expansion requires applying rigorous quantum field theory, or QFT, directly in curved spacetime. The short-wave mathematics produce mathematically infinite values in curved space. Only by formally isolating and subtracting these UV divergences can we mathematically determine if the universe survived its own birth. This is the one-loop effective potential for the Higgs field in curved spacetime. Notice two additions, the scalar curvature term, r, equal to 12 times the Hubble scale squared, and the Greek letter xi. R represents the geometry of spacetime. Since it's proportional to expansion, rapid cosmic stretching impacts the Higgs field's effective mass. Meanwhile, the coupling parameter xi dictates how strongly the Higgs reacts to that curvature, acting as the primary mathematical stabilizing force. But the equation is incomplete without accounting for the back reaction of the local, inhomogeneous field fluctuations inside this curved geometry. This graph plots the exact vacuum expectation values integrated across momentum. As we calculate for higher and higher momentum values on the right, the energy curve rapidly scales to infinity. This is a logarithmic UV divergence. In quantum field theory, this is a direct mathematical consequence of the expanding scale factor of the universe dragging on the quantum field. The bare equations dictate that the energy fluctuations are infinite. To extract the physical reality of the field's behavior, we must apply a precise mathematical filter called regularization. The necessary QFT method to cleanly subtract these inflationary UV divergences is adiabatic regularization. This secondary line represents the first step, calculating the lowest order WKB adiabatic approximation. This establishes a baseline measurement that shares the exact same infinite divergence as our physical field. By subtracting this adiabatic baseline from the exact field expression, the overlapping infinities cancel each other out. The UV divergence is mathematically eliminated. What remains is a finite, isolated area. This represents the renormalized vacuum fluctuations, the actual physical particle production effects caused by cosmic expansion. This renormalized value must now be fed back into our effective potential equation. It acts as a dynamic back reaction term, showing exactly how the field's own turbulence pushes against its structure. With adiabatic regularization, we finally have the exact physical magnitude of the field's back reaction. We can now plug in different values for gravity coupling to test if the Higgs potential survives the inflationary phase. We establish our first test condition by setting the non-minimal coupling, Xi, to an extremely small value, less than 10 to the negative third power. At this minimal value, the stabilizing curvature mass term in our equation is exceedingly weak. It lacks the mathematical weight to anchor the field against the kinetic energy of expansion. Meanwhile, the physical turbulence we just calculated, the renormalized vacuum fluctuations, creates a massive back reaction that completely overwhelms the weak stabilizing forces. This 3D topographic map shows the resulting Higgs effective potential. The mathematics show that the energy barrier confining the false vacuum is driven below zero. Without that barrier, the local Higgs field has nothing holding it in place. It classically rolls out of the electroweak state and plunges straight into the negative energy Planck scale vacuum. The macroscopic physical consequence of this local collapse is the sudden formation of an anti-de Sitter, or ADS, bubble. Inside this bubble, the physical laws that allow for matter and complex structures cease to exist. These ADS bubbles expand outward at the speed of light. Because they form constantly throughout the inflationary period, they will inevitably merge and consume the entire electroweak vacuum. If gravity and the Higgs field are barely coupled, the mathematics dictate that the universe collapses into a negative energy void before the Big Bang even concludes. We can attempt to solve this by testing the alternative condition. We assume a much larger coupling parameter. Psi is greater than 10 to the negative second power. This successfully reinforces the energy barrier and stabilizes the potential during inflation. However, surviving inflation immediately plunges the universe into a second, far more chaotic thermodynamic trap, the post-inflation preheating phase. During preheating, the primary field driving exponential expansion, the inflaton field, exhausts its outward pressure. It begins to coherently oscillate back and forth across its minimum energy state. This split-screen data visualization tracks the mechanics of preheating. Spacetime curvature is directly tied to the inflaton field on top. As the inflaton oscillates, the effective mass term on the bottom violently fluctuates between positive and negative values. The behavior of the Higgs field under these shifting conditions is governed by the Mathieu equation, which defines stability using a resonance parameter called Q. If Q is less than 1, the field operates in a narrow resonance regime. The Higgs fluctuations decay harmlessly alongside the continued expansion of the universe. But the high coupling parameter we use to survive inflation explicitly pushes Q above 1, triggering the tachyonic resonance regime. Inside this broad resonance band, the rapidly shifting spacetime curvature acts like a perfectly timed push on a swing set, exponentially amplifying the Higgs fluctuations. This tachyonic burst of kinetic energy instantly drives the field over the barrier and into the true vacuum, filling the post-inflationary universe with fatal ADS bubbles. A large gravity coupling mathematically saves the universe from inflation, only to guarantee its destruction by preheating resonance fractions of a second later. This phase space plot maps the ultimate thermodynamic fate of the universe, based entirely on these two competing variables, the Hubble scale of expansion and the coupling parameter Xi. Low coupling results in death by inflation. High coupling results in death by preheating. The severity of this trap depends entirely on the instability scale, lambda I. If expansion pushes the energy state above this precise threshold, the quartic term of the Higgs potential turns negative. If the Hubble scale exceeds this instability limit, the permissible safe zone for our universe is reduced to an incredibly narrow, highly specific mathematical band. Surviving both inflation and preheating requires landing exactly inside this microscopic parameter sliver. Under the current standard model alone, a stable universe is a statistical anomaly. These severe quantum field theory constraints strongly indicate that the standard model is incomplete. The math points to the necessity of undiscovered physics required to guarantee vacuum stability. Physicists are currently exploring theoretical solutions that fit these constraints, such as a direct coupling between the inflaton and Higgs fields, or hidden corrections operating at the Planck scale. The stable electroweak vacuum we currently inhabit is a physical artifact of successfully navigating conditions that mathematically should have destroyed it. The extreme geometry of the early universe weaponizes quantum fluctuations. Only through the rigorous application of QFT renormalization can we measure the razor-thin margin of our cosmic survival.